So you're given a chunk of soil, or you're in an environment somewhere, and you say, well, how's water going to move in this environment? You know, what's going to happen? Well, what we have to do is we have to characterize the soil. And what we're going to do to characterize the soil is we're going to use the soil characteristic curve. The characteristic curve. And what that is really trying to do is identify how water is retained by soil. So what we're going to do is on one axis, we're going to put the water content. And we'll use the symbol theta, which is the volume of water per volume of soil. You could also do this in terms of the mass of water per mass of soil. On this axis, we're going to put the pressure. And we're going to start at a pressure of 0. And at a pressure of 0, the soil is saturated. That means that there's no tension pulling water out of the soil. And notice that we go negative pressure at the top. So we're going to go from 0 to more and more suction or negative pressure. So what we have on this curve, we start with, when it's saturated, we call that theta sat. So that's going to be the theta sat. And that's going to happen at 0 pressure. And then, as we drain our soil, we're pulling the water out, it dries. And so the characteristic curve looks something like this. So this is then saying that somewhere here, we get to a residual saturation where no more water can be drawn out simply by trying to pull on the water films. What's that mean? That means that the water films are breaking down and we have isolated elements of water throughout the soil. So we have theta sat, theta residual. This we might call our water entry pressure, our air entry pressure, excuse me. So we call HAE is going to be the air entry pressure. That's when the water had been fully filling the pores, and when essentially the largest pores start releasing their water because the air is entering. And this is called the drainage curve. Okay? Now, when we're draining, it goes this way, but we can also fill the soil. And so when we fill the soil, we might start from absolutely dry soil. In this case, I'm going to start from dry soil. And I'm also going to end up with fully saturated soil. But what you can see is that these two curves are separated. That means that soil that has started saturated and dries versus soil that started dry and is saturated end up, for the same pressure, might have very different moisture contents. And this is called hysteresis. And hysteresis is very important, as you can see, because what the plants do is the plants apply pressure. They try to pull water out of soil. But if the soil was starting saturated, the plants might have a very easy time of getting the water out. Whereas if the soil had started from dry conditions, that same water content would be, they'd be at a much lower water content. So this hysteresis is a fundamental piece of the soil characteristic curve. And if we were wetting here, so we're wetting here, and then we decide to drain again, we can actually get another curve coming from that curve, and then we say, oh, no, let's start drying again. So you can get these systems of hysteretic curves so that you can have almost any number of moisture contents for that given same pressure. So when we characterize soils, first off, we say, what are the characteristic curves of this soil that define when it's fully saturated draining and when it's fully dry wetting? And then, with those two curves, we can predict everything else. And this is how we take a piece of soil and characterize its relationship between water content and pressure, which is exactly what plants and any sort of infiltration processes or any other thing that you want to describe with respect to the hydrology of soils would be initiated.